In this lecture, we are going to discuss about linear phase FIR transfer functions. As we discussed in the previous lecture that in order to avoid phase distortion, we need systems or filters, in fact, that can preserve the phase of an incoming signal once it is passed through it. So in this regard, we also notice that it is impossible to design an IIR transfer function with an exact linear phase. Though we developed a solution where we cascaded the IIR filter with an appropriate order all-pass filter, all-pass system to have linear phase characteristics. But here we are specifically talking about only a single filter where we don't do any cascading. So in that context, IIR transfer function cannot have exact linear phase. However, it is always possible to design an FIR transfer function with an exact linear phase response. But for that, we have to take into account certain things. So here we will be considering a FIR transfer function h of z with related impulse response h of n. So as you can see here, the z transform of a length n plus 1 FIR filter is shown here. So order of the filter is equal to capital N. Now if we require that this FIR filter has a linear phase, so in that case its related frequency response must be of this form as shown here, where the frequency response is written as a product of an amplitude response times time a phase response. The amplitude response, as we have previously discussed in one of our earlier lectures, that amplitude response is also known as a zero phase response because there is no specific phase component present in this case. However, here in the case of linear phase response, the zero phase response or amplitude response is multiplied by a phase function shown by this exponential, where c and beta are some constants, and soon we will see that what is their significance. Now if we have a real impulse response, we already know from the symmetry relations of discrete time Fourier transform that the magnitude response is always an even function of omega, as depicted by this equation. And if we take the absolute of amplitude response, it becomes equal to the magnitude response. And therefore, the amplitude response is either an even or odd function of omega. That is, if we replace omega with minus omega in the representation of amplitude response, so both of them can be related as the h of minus omega. The symbol shown above h is known as brief. So h brief of minus omega is equal to plus minus h brief of omega. If the amplitude response is an even function, so plus sign will be present here, and if amplitude response itself is an odd function of omega, then minus sign will be intact. So if we require that an FIR filter have a linear phase, then there are two conditions that needs to be met, or there are two different ways where we can realize an FIR filter with a linear phase characteristics. So in this case, if the FIR filter has an even amplitude response, which is equivalent to saying that it has a symmetric impulse response. where the center of symmetry in the case of a causal filter will be exactly located at small n equal to capital N by 2, whereas in the case of a causal system, the center of symmetry will exist exactly at small n equal to 0 in terms of the impulse response of the system. So if the system has a symmetric impulse response, which is depicted by this equation, where we are considering a causal system, a causal FIR system of length n plus 1 and order n. Therefore, the center of symmetry will exist at small n equal to n by 2. So this system has a symmetric impulse response, that is, with reference to the center of symmetry, the impulse response coefficients are similar. So we can realize linear phase characteristics in the case of an FIR filter if it has symmetric impulse response. And secondly, it is also possible that if the impulse response of an FIR filter is antisymmetric, that is, the impulse response coefficient around the center of symmetry exhibit negative symmetry, that is, the coefficients are same but with different sign, then such a filter will have an odd amplitude response, and this filter will exactly realize linear phase response as well, or it will have linear phase characteristics. Again, the filter is causal, have a length n plus 1 and order n. Once the length of the impulse response is even, that is, the filter has an odd length and it is antisymmetric FIR filter, so in that case the center of symmetry or the center sample at n equal to n by 2 for a causal filter will be exactly 0. This is equivalent to saying that an odd function always has a center of symmetry value, or amplitude at center of symmetry is exactly 0. Now, the linear phase FIR transfer functions can be categorized into 4 types as shown on this slide, and they are respectively known as type 1, type 2, type 3 and type 4. In the case of type 1, it has always an order which is even, as shown here for n equal to 8. Therefore, the length of this response will be odd, that is, in this case it will be 9. The center of symmetry, because the response is causal, the center of symmetry will be at n equal to small n by 2, which is 4 in this case. And you can clearly see that around this center of symmetry, the coefficients of the impulse response exhibit same amplitude. In the case of type 2 linear phase FIR transfer function, the length is even and order of the response is odd. Therefore, we can imagine the center of symmetry at n by 2, which is 3.5. However, the x-axis only can have integer values, so therefore we can only imagine that the center of symmetry lies here. Physically, it is not any value in this case. And around this, you can clearly see that the impulse response coefficients are same. Therefore, this is again a symmetric impulse response, as was the case in the type 1 linear phase transfer function. However, both have a difference that their order, in one case, that is in type 1, the order was even, and in the type 2 case, the order is odd. Moving on to the type 3. So type 3 filter have even order and odd length. Center of symmetry is at n equal to n by 2, that is 4 in this case. And as you can see that the sample at this center of symmetry has exactly 0 amplitude. And around this center of symmetry, the impulse response coefficients exhibit anti-symmetry. So their sample values are exactly opposite to each other, 1 and 7, 0 and 8. Similarly, in type 4, we have odd order and even length. Again, we can only imagine the center of symmetry being at 3.5, which is definitely not true because this is not a physical value on a discrete axis, but just for our imagination. And around this, we notice that the impulse response coefficients are exhibiting anti-symmetry. So 3 and 4, 2 and 5, 1 and 6, 0 and 7. So all these 4 types of linear phase FIR transfer functions, which are either symmetric or anti-symmetric and have difference in terms of their orders or equivalently in their lengths, so they exhibit exactly linear phase characteristics. This is not necessary, always not necessary that the response represents a causal filter. The filter can be acausal as well in this case. However, in that case, the center of symmetry shifts from n equal to n by 2 to n equal to 0. Now we will discuss all these 4 types of transfer functions one by one. So in here we, as an example, we consider a type 1 system which has symmetric impulse response with odd length and even order, and we select order equal to n equal to 8 for simplicity. This is the related transfer function of this filter because there are 9 different coefficients starting from h0 till h8, and the power of the highest power in terms of z inverse is 8. So that depicts that this is a order 8 response. Now because the filter has a symmetric impulse response, therefore h0 corresponds to h8, h1 corresponds to h7, h2 corresponds to h6, and h3 corresponds to h5, whereas h4 is the center of symmetry. So we combine all like amplitudes, and as a result of it we can rewrite the transfer function as shown this equation in green color. So we have combined all like coefficients because h0 is equal to h8, so it's simple to write only h0, and h1 because h1 is equal to h7, so we are combining here h1 and h7, taking h1 as a common factor and so on. Now we want a common multiple in terms of powers of z inverse. Therefore we select z power minus 4 as a common factor from each of these terms. Therefore, if we select z equal to minus 4 as a common factor from first term, so we will have a z power 4 plus z power minus 4 inside round brackets. Similarly, if I take common z minus 4, so I will have z power 3 plus z power minus 3 as common factor in second term. Here I will be left with z power 2 plus z power minus 2 once I take z power minus 4 as a common factor, and in this case I will be left with z plus z inverse if I take z power minus 4 as a common factor. There is already a z power minus 4 present in this last term. Therefore, we can take z power minus 4 as a common factor from all the terms. Now, if we evaluate this transfer function, because we are talking about a stable filter, so if we evaluate this transfer function on the unit circle, that is, we substitute z equal to ej omega. So the expression can be simplified as e power minus j4 omega for z power minus 4, and these two terms, that is z power 4 and z power minus 4, this will become 2 cos 4 omega multiplied by h0. Similarly, 2h1 cos 3 omega, 2h2 cos 2 omega, and 2h3 cos omega plus h4. As a result of it, we get the equivalent frequency response of this system. Now you can clearly see that frequency response has been decomposed into two factors. One is this phase factor, e power minus j4 omega, and all the terms written inside these two curly brackets represents the amplitude response in this case, and you can clearly see that amplitude response is a real function of omega, because we have only terms which such as cos 4 omega, cos 3 omega, cos 2 omega, cos omega present in this case. Therefore, the phase function can be written as e power minus, the phase function is minus 4 omega because it is the multiple with j, plus there is some constant term which in some cases is equal to 0 and in some cases it becomes equal to pi. For simplicity, we can take it 0, and we can see that the phase function is a linear function of omega. So this is a linear equation, and if I take the negative derivative of this phase function, I will get a group delay of 4 samples. Therefore, if I have a type 1 FIR filter which exhibits linear phase characteristics, it will introduce a delay of 4 samples once a signal is passed through it, or in general a delay of n by 2 samples is introduced by this filter. So this is a condition which can only be met in the case of linear phase characteristics, if the system obeys linear phase characteristics. In general, we can write the frequency response of a type 1 FIR filter using this form, where the phase function is always n omega by 2 multiplied by a amplitude response, which is also known as a zero phase response. And general form of amplitude response is shown by this equation, where you can substitute any value for capital N, which must be even in this case, and you can compute the related amplitude response for a filter of any order, which is a type 1 FIR filter. Here is an example of a type 1 FIR filter. As you can see, all the terms in this case, that is, they are multiplied by a common factor 1 by 6. If I take it inside, I will have 1 over 12, 1 over 6, 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 plus 1 over 12 as multiplying factors in all terms. Now, the highest power in Z inverse is 6, therefore capital N has a value of 6 in this case, and you can clearly see that the first term has an amplitude of 1 by 12 and the last term has an amplitude of 1 by 12. So both of them correspond to each other. Similarly, the coefficient of Z inverse will be 1 by 6 and of Z minus 5 will be 1 by 6. Both of them are equal and correspond to each other. And in a similar manner, the coefficient of z minus 2 will be 1 by 6 and z minus 4 will be 1 by 6, and they correspond to each other, whereas the coefficient of z minus 3 is 1 by 6 and it is exactly at the center of symmetry. So the response is a length 7 response. It is symmetric and therefore it is a type 1 FIR filter. In the case of type 2, the impulse response is still symmetric, but one subtle difference as compared to type 1. Here we have even length. Therefore, the degree of n is odd, or in other words, the filter will have an odd order. That is n equal to 7 in our case, as we have selected an example in the previous case as well with an order of 8. Again, we explicitly expand the transfer function in the powers of z inverse. Here h0 corresponds to h7, h1 corresponds to h6, h2 corresponds to h5, and h3 corresponds to h4. Again we combine them together, and later on we take the common factor. Now the common factor should always be equal to z power minus n by 2. So because capital N is 7 in this case, therefore we will take z power minus 7 by 2 as a common factor, not only in the first term but also in all other terms. Having taken z power minus 7 by 2 as a common factor from first, second, third and fourth term respectively, we are left with this expression, and z power minus 2 is a common factor. Again, computing the transfer function on the boundary of unit circle such that it converts into the related frequency response by substituting z equal to ej omega, we will get frequency response as e power minus j7 omega by 2, which will be our phase function in this case, and all the terms in the curly bracket, that is these four terms, will be converted into cosines such that the first term will be 2h0 cos 7 omega by 2, the second term will become 2h1 cos omega 5 omega by 2, the third term will be h2 times cos 2 cos 3 omega by 2, and the last term will be h3 times 2 cos omega by 2 as shown in this slide. So the phase function in this case is minus 7 omega by 2, and amplitude function comprises 4 terms which are shown inside the curly brackets, and once again we can see that the amplitude response is a real function of omega. If we take the negative derivative of the phase function, so we will get a fractional group delay of 7 by 2. Therefore, this filter, that is type 2 linear phase FIR filter, will act as a fractional delay filter. That is, it will introduce a delay of 7 by 2 samples once a signal is passed through it, because 7 by 2 is not physically measurable in the case of digital system or discrete time system. Therefore, such a system is known as a fractional delay system. And at a later part of today's lecture, we will see that this fractional delay characteristics limit its application. Again, we have a general form of frequency response for a type 2 FIR filter and the related generalized amplitude response, where again you can substitute any value of capital N, which must be odd, and can compute the related amplitude response for type 2 filter. Next comes the type 3 filter, which has antisymmetric impulse response with odd length. Therefore, the order will be even in this case again. However, due to antisymmetric impulse response, the corresponding coefficients, that is H0 and H8, which are both same, will have amplitude which is opposite in sign. Therefore, once we combine those terms, we will have this combination. Similarly, for Z3 and Z7, Z2 and Z6, and Z1 and Z5. The center sample will be 0 because we have a odd length filter with antisymmetric impulse response, so center sample will be 0 in this case. Therefore, you don't see any extra term in this case. Once again, computing the transfer function on the boundary of unit circle and replacing z with e j omega, we will have corresponding phase function as e power minus j 4 omega, because we have taken it as a common factor as we did in the case of type 1 filter as well. And inside we will have 2h0 j sine omega, because we have to multiply this term with multiply and divide this term with 2j to make it or convert it into a sine, and the same thing will be done in other cases. So there will be a factor 2j common in all these terms, whereas we will have sine 4 omega, sine 3 omega, sine 2 omega and sine omega. So that j factor can be written as e power j pi by 2. Using Euler identity, this will give us a cosine pi by 2 plus j sine pi by 2, which will be equal to j. And these are the terms which are representing our amplitude response inside curly bracket, and phase function is given by minus 4 omega plus pi by 2 plus some constant beta, which is either 0 or pi. Taking the negative derivative of the phase function, we get group delay as 4, which is a constant group delay again, as we also noticed in the case of type 1 filter. So if a signal is passed through a type 3 FIR filter, it will produce a delay of 4 samples. Here we can see that the generalized amplitude response of a type 3 FIR filter is given by this equation, where you can replace capital N with even value and can compute it for any order. In the case of type 4, the response is antisymmetric and length is even, therefore order of this filter will be odd. Once again, combining the like terms and taking the z power n by 2 as the common factor, as we did in the case of type 2 filter. However, here the difference is the response is antisymmetric, so therefore you notice minus sign after combining all the like terms. Once again, the related frequency response computed on the boundary of unit circle by substituting z equal to e j omega will be given by e power minus j 7 omega by 2 for this term. E power j pi by 2 again appears because there will be a 2j factor appearing in all the 4 terms because of converting all these terms into sine. So we take it as a common factor, and rest of the terms will be 2j sine 7 omega by 2, 2j sine 5 omega by 2, 2j sine 3 omega by 2 and 2j sine omega by 2. 2h3 sine omega by 2. The phase function is given by minus 7 omega by 2 plus pi by 2 plus beta, and beta can be either 0 or pi. The negative derivative of the phase function gives us a fractional group delay. Because of this, type 4 filter is also a fractional delay filter, and the presence of this fractional delay limits its applications. The generalized amplitude response of this filter is shown by this equation. where substituting capital N as any odd value, you can compute the related amplitude response. So all four cases, we have noticed that the generalized frequency response is written as a product of phase response type times the amplitude response, where phase function is always equal to n omega by 2, which is a linear function of omega. Here we can see in this example a type 1 FIR transfer function, where you can easily see that the first and the last coefficient are same, the second and the second last are same, similarly the third and third last are same, and this is the center of symmetry. The value is 6. So we can directly write its related amplitude response by using the generalized equation of amplitude response of type 1 filter by substituting capital N equal to 6, and the related phase function, because order is 6, so phase function will be minus 3 omega. Now we consider a type 1 filter which has got coefficients which are opposite in sign compared to H1 of Z. Still it's a type 1 filter, so you can see that the related coefficients are 1 and 1, minus 2, 3, 3, and center sample is minus 6. So such a filter, although the sign of the coefficients have changed, it is still symmetric and type 1 FIR filter. The value of the coefficient is same, so its amplitude response will be the negative of the amplitude response of first filter. So therefore what we have done here is that we have simply given a phase shift of pi to H1 of Ej omega, and because of that the related new system has got amplitude characteristics which are negative of that of the filter H1, but both of them are type 1 filters. The related phase function in this case, theta 2 of omega, is minus 3 omega, and this pi appears because of the presence of a minus sign in the amplitude response, because we know that pi, a minus sign can be written as Ej pi, and Euler identity permits us to write it as cos pi plus j sin pi, which will be always equal to minus 1. The magnitude response of both the filters, that is, if we apply absolute on amplitude response on both sides, so it becomes the magnitude response of the systems, they are same. However, their phase responses exhibit a phase difference of pi degree, pi radians, as shown here. So H1 and H2 of Z, because their transfer functions have the coefficients which were equal in magnitude but opposite in sign. Similarly, this can be seen in the case of a type 3 filter given as H3 of Z. The related phase function is given here as minus 3 omega. The related amplitude response is given here as shown. And if we change the sign of the coefficients of this filter, we will get again a type 3 filter. However, this type 3 filter will have a response, amplitude response, which is negative of the amplitude response of H3, and it will have a phase characteristics where we will have, because it's a type 3 filter, so the phase function already has pi by 2, and because of the presence of this negative sign there will be a factor of minus pi, so plus pi by 2 minus pi makes it minus pi by 2, So the phase function is given by theta 4 of omega for h4 of ej omega is given by minus 3 omega minus pi by 2. However, the related magnitude responses of both the filters, which are equivalent to taking the absolute of h4 and h3, they are similar. So they exhibit a phase difference of pi by pi in their representation. So group delay in each of the case of type 1, type 2, type 3 and type 4 filter is exactly n by 2. So we have linear phase characteristics which can be realized provided if the system exhibits symmetric or anti-symmetric impulse response, and it is an FIR system.